Hello everyone, what I want to do in this short video is explain where on earth this formula comes from. Um, and as I mentioned in a prior video, that as long as you have positive cash flow, so um, um, all of the payments for your annuity are positive. So the setup is you're paying money right now for payments at the end of each period or at the beginning of each period, um, and all of those payments are positive, then the Macaulay approximation is always better than the first order modified approximation. So I should say the first order Macaulay approximation. And it is called first order because it's actually, as we'll see in a second, based off of a first order approximation for kind of funky function, but it is nonetheless based off of the first a linearization. So it's the first term in Taylor's theorem. Okay. But yeah, so this first order Macaulay approximation is always better in that situation than the first order modified duration approximation given here. I'm sorry. Where is it? Yeah, sorry. Given right here. This is my first order modified approximation. All right. And this is actually proven that it's always a better approximation in this PDF written by Robert Alps. It's actually been cited a few times in the research literature and finance and insurance mathematics. I'll put a link to this in the comments, but yeah, it's very technical, so I don't think it's really worth it to. Um, yeah, so it's in this Appendix C demonstration that first order Macaulay approximation is more accurate than first order modified approximation. Takes a few pages to do it actually, but yeah, it might be interesting if you're kind of a theoretically math oriented person. Anyway, so I don't want to get into that. Thought about it, but no, definitely not. So let me just explain where this even comes from. That's my goal here. In particular, having an exponent of the Macaulay duration. Why? Okay, so the answer is as follows. I'm going to look at the following function, which is the price of an annuity at this interest rate I times 1 plus I to the Macaulay duration at some given interest rate I0. Okay. So I is sort of like my new interest rate that's close to I0, but I'm still thinking of this as a function of I. So I claim that G prime of I0 is 0. Okay. And this is pretty easy to do. Let's just do this by the product rule. So it's first times the derivative of the second. So this is just a power rule. Really, I'm doing the derivative of 1 plus I times, which is just 1, times, well, drop the power, subtract 1 from the exponent. Or drop the exponent, subtract 1 from the exponent. But it's really just a power rule. So it's Mac D I0 times, I'll even put another parentheses here, lots of parentheses. Mac D I0 minus 1 plus Well, derivative of the first times the second. 1 plus I, mac d, I0. I don't know where that came from. Sorry about that. All right, and so this is going to actually make my linear approximation for G just incredibly simple. And that's where this Macaulay, first order Macaulay approximation is going to come from. All right, so plug in I0, we get so first, before I do anything, what is this? This is -1 plus I P prime of I0 over P of I0. Okay, ooh, sorry about that. Pen kind of went nuts there. All right, so this is great because I cancel one of the. Okay, so let me do one thing right here. So this is a general derivative. So let me plug in I0 into this derivative. So I have P of I0. Sorry, this was supposed to be an I0. My apologies. This is Macaulay duration at I0, so that was supposed to be I0 from the start. Again, my bad. So I0's here. All right, so let me just simplify this because I want to keep, particularly, I want to keep this on the screen here. So the P of i's cancel. Well, I have a -1 plus I0, then 1 plus sorry, should be. Forgot to put I0 here for I. And I'm plugging in I0. Right, so these go away. So let me just erase these. This becomes, well, multiply -1 plus I0 by 1 plus I0. You add 1 to the exponent. So you get rid of that. Well, you still have, so the minus didn't go anywhere, and you still have minus P prime of I0, and that's all that's left. Okay. Well, this is P prime of I0, 1 plus I0, the Mac d I0. So these two just entirely cancel each other out. You have minus this plus this, and that's exactly 0. So, yeah. So what does this tell me? So let me do the linearization of G at I0. So it says G of I is approximately G of I0 plus G prime of I0. Oh, 1 second. Well, all this stuff, we don't care about this because this here is 0. So this is saying g of I is approximate g of I0 as long as I is close to I0. So what does that mean? So remember, this is what g of I is. So it's saying P of I, more issues here. 1 plus I, mac D of I0. Okay. This is blue, G of I. Approximately plug in I0 for I. Move this up a bit. And this is G of I0. And we get our formula by dividing by 1 plus I to the mac D I0. And we have the same exponent, so I can just make it as a fraction. So P of I is approximately P of I0 by dividing by 1 plus I to the mac D I0. 1 plus I0 over 1 plus I mac D I0. And that is exactly what the Macaulay approximation is. First order Macaulay approximation. And the importance of mac D I0 in the exponent is otherwise, this is just by definition, this works because you do the product rule, and just by definition of mac D of I0 as 1 plus I minus 1 plus I0 times P prime at I0 over P of I0, everything cancels out. Any other exponent and it just wouldn't work. This calculation would not give you 0. This would stay the same regardless of what exponent it is. This would just not be equal to this if we did not have the special exponent. So yeah, that's it. That's where this comes from. Just linearization of G at I. Doesn't really tell you why this is better than first order modified approximation, but yeah, I've spent quite a few hours looking for a concrete explanation, or not concrete, but it's not the right word. A clear kind of commonsensical reason why, intuitive reason why, and I couldn't find it. You just have to plow through some math. Nothing you can't really understand if you've taken Calc 2 and Taylor's theorem, but well, anyway, hopefully this was helpful, and yeah. So yeah, like the video on Macaulay duration as a weighted average, you really don't need this video. Not useful really necessarily for calculations. It's just where on earth does the Macaulay approximation come from? The first order Macaulay approximation. All right. And I should mention there are second order approximations using second term and Taylor's theorem. I haven't seen it on the sample exam FM problems. So I guess they're not really testing it anymore, but they are a thing. They're more complicated, a lot more complicated for Macaulay approximation. But anyway, so long, take care. Almost done. Bye-bye.